Tune HNSW for best recall and low latency. By the end, you will know how efSearch affects both recall and response time. You will see a tiny reproducible pipeline that computes exact neighbors, builds an HNSW-like entry, runs efSearch limited re-ranking, and picks the smallest EF that gives top recall. You will also learn how to measure latency and trade it off against quality. I'm Professor Pi, teaching search and IR from basics to advanced in simple Python. HNSW is a graph-based approximate nearest neighbor method. It is popular because it finds good nearest neighbors fast on large vector collections. People reach for HNSW when linear scans are too slow but exact answers are still important. The trade-off is control knobs like efSearch that change how many candidates we examine and therefore how often we find the true nearest neighbors. Too small like efSearch and you lose recall. Too large and you pay in latency. Think of efSearch as the number of people you ask for directions before choosing the winner. Recall is the fraction of true nearest neighbors you recovered compared to an exact ground truth list. Latency is how long the whole search takes. Our goal is simple. Find the smallest efSearch that still gets maximum recall while keeping search fast. We will walk through a concrete tiny example so the effect is visible. First, we compute an exact baseline on a small two-dimensional set. Then we create an HNSW-style entry and a deterministic candidate order. Next, we simulate efSearch limited re-ranking to approximate top 3 neighbors. After that, we measure recall at 3 across different efSearch values. Finally, we pick the smallest EF that reaches the highest recall. Now we compute the exact baseline. This snippet computes an exact k nearest neighbor baseline on a tiny two-dimensional dataset, which we use as ground truth for everything else. It walks through pairwise distances between every query and database point, and then sorts to get the true top 3 neighbors for each query. This exact baseline is slow at scale, but perfect for evaluating recall on a toy set. Use this as the reference, so later we can say precisely what fraction of those top 3 we recovered when we switched to the approximate HNSW-style approach. Now we build a simple HNSW-style entry and ordering for candidates. This example establishes an HNSW-style entry point and a deterministic candidate ordering that the simulated search will traverse, so we can control the candidate stream without requiring a full HNSW implementation. It creates a layered graph idea and a ranking of nodes to visit, which mimics the breadth of candidates HNSW would expose. By changing the candidate order, we can simulate more or fewer relevant vectors being examined early. This makes the later efSearch parameter meaningful, because efSearch will limit how many of these candidates we actually re-rank. Next, we limit re-ranking by efSearch to see the core trade-off. This code performs efSearch limited re-ranking to approximate the top 3 neighbors by only computing exact distances for the first efSearch candidates from our ordered stream. It shows how increasing efSearch expands the candidate pool, which usually improves the chance of including the true neighbors before re-ranking. If you double efSearch, you will likely increase recall, but also increase the distance computations and the measured latency. This illustrates the core effect. efSearch trades CPU and time for better quality in the final ranked results. Now we sweep efSearch and measure recall at k equal to 3. This snippet quantifies recall at k3 across several efSearch values by comparing the approximate top 3 to the exact baseline and counting matches. It records both the recall fraction and the time taken for each efSearch value, so you can visualize the trade-off curve. The idea is to produce a simple table or plot where recall improves with efSearch up to a plateau, while latency grows roughly linearly or sublinearly. This makes it easy to pick the elbow where extra candidates stop paying off. Finally, we pick the most efficient efSearch that still achieves peak recall. This snippet picks the smallest EF that achieves the highest recall efficiently by scanning the results from the previous sweep and selecting the first efSearch value, whose recall equals the maximum observed. It also returns the associated latency so you can report a clear operating point. This produces a single recommended efSearch that balances quality and speed for the toy corpus. The same approach generalizes. Run a sweep, find the recall plateau, choose the minimal efSearch on that plateau to save time. Recap: HNSW is a fast approximate neighbor method where efSearch controls candidate count. Use an exact baseline to measure recall and latency precisely. Caveat: the optimal efSearch depends on your data and your latency budget. There is no single universal value. Next step: run the same sweep on a larger corpus and add timing for cold and warm queries. Or try a different distance metric to see how the efSearch curve changes. If practical IR and measured trade-offs help you, subscribe and watch the rest of the search videos.